All right, pre-calc students, we're moving on. Chapter 7, Part 1, review. Excuse me. Please make sure that when you're filling out your note card, it has some of this stuff on it. All right, these were our learning targets and the different topics. All right, and so here we go. First thing we need to remember when we're talking about inverses, if I ask you for the inverse, there are very specific places where I would like you to look. And the reason is because I just want there to be one section for positive options and one for negative. All right? So if we think about it, sine, if we want both a positive and a negative section and only one of each, well then what I'm going to say is I'm going to go from negative pi over 2 to pi over 2. Like this. And I'm going to say no, 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 no to quadrants 2 and 3. Alright? So if I give you a ratio, then I'm looking for an angle within these two sections. And hopefully that makes sense again, because I want just one area where it can be negative and one area where it can be positive. Alright? Well, it's the same thing with cosine, but now, because cosine goes with x values, we don't go from negative pi over 2 to pi over 2. We go from 0 to pi. Alright, and how do we know that? Well, because in quadrant 1, and I should put this 1 and 4. Alright, I know that I use 1 and 2 because in quadrant 1 my cosine is positive, in quadrant 2 my cosine is negative, and then I don't care. I shouldn't say I don't care, but I only want there to be one spot, one option. Alright, so those are the two locations where the inverse cosine should lie. And then tangent, we use sine, the same as sine. Alright, so again we're going negative pi over 2 to pi over 2, something like this. So this is again quadrants 1 and 4. Goodbye. No, 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 no. Alright. And really, guys, the reason that we could have used 1 and 2, but one of the major reasons why we don't use 1 and 2 is because right at pi over 2, excuse me, right at pi over 2, our tangent would be undefined. So instead of using this undefined location, we just use this nice area right here. Okay? So again, if I ever ask you for the inverse sine, your answer better be between negative pi over 2 and pi over 2. So let's write that right now as well. Sine must be... Whoa, I'm throwing my pen. Hold on. Alright. Must be between negative pi over 2, must be between 0 and pi, and then again tangent is between negative pi over 2 and pi over 2. Those are kind of the domains that you should keep in mind. Alright, so now let's put this to work. In something like number 1, I see the inverse sine of tangent pi over 4. So this is one of those multiple step problems where we need to first figure out what tangent of pi over 4 is. Well, if my angle is pi over 4 and I want the tangent of it, well, pi over 4 is here. Oh, I know that that's just root 2 over 2 divided by root 2 over 2, or the tangent is 1. Alright? So now I know that I want to find the inverse sine of 1. And again, please remember, guys, this number, if you're taking the inverse sine, then this is not an angle. This is the ratio already, okay? So I'm looking for where the sine is going to be 1, or I'm looking for where y is 1. Hopefully, we remember that sine is 1, or the y value is 1, at an angle of pi over 2. Alright? Okay. When we take the inverse sine of negative 1/2, similar concept, I need to draw my angle where y is negative 1/2. So I know I'm going to be over here. Please remember, I'm not going to be over here. Why? Because that's not in the correct area. So I just want this angle right here. Now hopefully you guys know that when the y's that are 1/2, those are all my pi over 6's. So a lot of people, maybe after chapter 6, would have said that our answer was 11 pi over 6. What is the problem with saying 11 pi over 6? 11 pi over 6 is not between negative pi over 2 and pi over 2. I do not want 11 pi over 6. I want you to say, instead of going all the way around into quadrant 4, I just want you to go back a little bit. This is just negative pi over 6. All right? When we write finals, do we write questions that might be, I don't want to say misleading, but do we give answer options that might be a little tricky? Yeah, we do. All right, so you better be on the lookout for something like this. All right, our next one, we actually have to do one of our little tricks. We have to first remember, well, tangent, whenever we're talking tangent, that's already the ratio of y over x. So I'm going to rewrite this as a fraction. But then what I'm also going to do is I'm going to say that I actually have negative root 3 over 2 over 1/2. And if you remember correctly, we don't know where y is negative root 3. We don't know where x is 1 on the unit circle, but we do know where these values are, okay? So we got to remember that little trick for tangent, that we can always put them over to, all right? Because now I can go ahead and I can sketch this. Where is y going to be root 3 over 2? Where is x going to be 1/2? Well, those are my pi over 3's, all right? So I could be here, I could be here, here, right? I know it's going to be a pi over 3. The important thing to understand is, well, a couple things. One, it's negative, okay? So I know it either has to be in quadrant 2 or 4. But please remember, inverse tangent, should not be in quadrant 2. It needs to be between negative pi over 2 and pi over 2. So that's quadrant 4. So I know I'm going to draw my ray right over there. So I knew that this was a pi over 3. My only thing I have to remember is I'm not going all the way around to 5 pi over 3. I'm just going backwards, negative pi over 3. So my final answer should be negative pi over 3. All right, last one of these. Please remember, if you ever see arc cosine, that really just means inverse cosine, root 3 over 2. Okay, and so we need to know where is the cosine root 3 over 2, or where is the x value root 3 over 2? Positive root 3 over 2. So please remember, cosines should be in quadrants 1 or 2, and because this is positive, quadrant 1. Any of my root 3 over 2 cosine values, okay, when x is root 3 over 2, that's a pi over 6. And because this is just in quadrant 1, the answer is just pi over 6. All right, so that was a refresher on this stuff. You got to be able to work with the unit circle. Very, very important. All right. Okay. So as we move down to number 5, this is one of those abstract ones. Actually, like, we did pretty well on these, I remember, during the chapter, so I'm hoping that this is more of just like a little refresher. If we have the inverse cosine of 2u, like, I don't know where that is on the unit circle, so I can't use a unit circle. I'm going to have to sketch this picture out, and what we need to remember is, well, we're going to call cosine 2u theta, right? Because that's our angle that we're trying to find the sine of. So we're replacing this with a theta towards the end. We still have some work to do. Because if you remember, inverses are just kind of undoing things, right? Like, I can rewrite this. If I'm taking the inverse cosine of this ratio to get this angle, well, then I can also write the cosine of the angle is equal to the ratio. All right? Hopefully that rings a bell. If you're taking the inverse cosine of a ratio, you get an angle. If you're taking the cosine of an angle, you get the ratio. All right, so now we can sketch this picture. All right, now we can sketch this picture. So I'm going to draw a little triangle here. I'm going to say that I have theta, and I know that the cosine is 2u over 1. So that means my adjacent and my hypotenuse are known. I know the adjacent, I know the hypotenuse, and this, of course, is a right triangle, so we can use what? We can use Pythagorean Theorem. Alright, I'm going to say that 2u squared plus, maybe I'll put a b there, okay, plus b squared, I should never put a b again because my b's always look like 6's. Alright, b squared equals 1 squared. Alright, so if we keep going here, 2u squared is 4u squared plus b squared equals 1. I'm going to rewrite this as 1 minus 4u squared, and I'm going to square root both sides. Please, please, please remember, guys, this is not a perfect square. You cannot square pieces separately, all right? Because 1 minus 4u squared, that's a quantity, all right? The only way you could take the square root of that is if this factored into two identical terms, but it does not, all right? So I'm going to say just that b is equal to 1 minus 4u squared. I'm going to leave it like that, and I'm going to put it into my picture, okay? 1 minus 4u squared. All right, so now, we're just about done. I know that I want the sine of theta, right? And here's my theta. So if I want the sine, then instead of doing adjacent over hypotenuse, I'm going to do the opposite over hypotenuse. So I'm going to take my opposite side that I just found. I'm going to put it over the hypotenuse. Oh, and I'm pretty much done, right? My final answer would just be the square root of 1 minus 4u squared. Okay? Okay, we're getting there. The last section of this chapter was identities. All right, you're not going to have to verify any because this is a multiple choice test, so you're not going to have to actually go through any of the steps to get one side to equal the other, but I am going to ask you to simplify. All right, I'm going to ask you to simplify, and I know you didn't like simplifying as much, but we're here to go back over some of our tricks that will help us simplify properly. All right, so the very first trick, the one that I think I tend to use the most, is always get in terms of sines and cosines. All right, that for some reason I like thinking in terms of sines and cosines the most. All right, the next one that is pretty important would be what do I do? I'm gonna do. I want to maybe go in conjugates. All right, conjugates. We use conjugates. We multiply by conjugates because when we use conjugates, we get difference of squares. And when you have difference of squares, you get ... identities. And I'm going to actually put the word Pythagorean, okay? Because a lot of the times when we use difference of squares, we end up getting one of those like 1 minus sine squared or 1 minus cosine squared, blah, 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 blah. And then we can use those to kind of simplify, all right? So hopefully this makes sense. This conjugate step actually leads to our third. So identities are super important. Oh, yep. When we have fractions, a lot of the times we're going to need a common denominator. All right, and then a last one that I don't know if I really have to write, but sometimes is good. Distributing or distribute slash factor. All right, so I'm going to put that list. I think that's a good list and just kind of some steps to think about as you are simplifying your identities. All right, so here we go. And actually, I already see right here towards the top, sine squared. All right, we should probably talk about those Pythagorean identities. All right, so up at the top, I want you to remember that sine squared plus cosine squared always equals 1. All right, that was the big one. That one is one that we need to remember. Now, both of the other ones work right off of this. If you want to memorize them, that's fine. What I'm going to basically do is I'm going to say, well, I want to divide every single one of these pieces by sine squared. Now, I'm not going to show that right now, but I'm going to put right here, if I divide by sine squared, ... well, then I'm left with 1 plus cotangent squared equals cosecant squared. Alright, and hopefully that makes sense, right? If I divide every single piece by sine squared, I'm going to get sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. 1 over sine squared is cosecant squared. Alright, well, the other option is to divide by cosine squared. Alright, if I do that, well, then I'm left with tan squared plus 1 equals secant squared. Alright, so these, 1, 2, 3, those are our 3 Pythagorean identities that we should probably keep in mind for this page. Holy cow, I'm going so super long. This is terrible. I'm sorry, guys. Let's get to work. Alright, so this first one, I see one fraction. I'm thinking that I already see sines and cosines, so yeah, I think I probably need to get a common denominator. Alright, so I'm going to say, well, if this is 1 over 1, well, then I'm going to multiply top and bottom by 1 plus cosine. 1 plus cosine. Oops, I forgot theta. Theta. Alright, sorry about that. So when I do that, and I clean it up, I know that because I have the same denominator, I can just write this. Sorry, guys, the camera's kind of in my way. Okay, I know that everything's just going to be 1 over 1 plus cosine theta. Alright, well, what did I have in the first numerator? I had 1 plus cosine, and then I had a minus sine squared. Okay, interesting. Alright, I need you guys to recognize, and if there's one thing you learn and take away from pre-calc, it is that you cannot cross off these 1s and you cannot cross off these cosines. Oh my gosh, right? This entire numerator is it's 3 different terms, okay? You cannot, it's an entire quantity. That's the word I'm looking for, right? Like, this entire thing is together. This entire thing is together. Things only cancel if the entire quantities are the exact same, all right? So don't cancel off the 1s. Don't cancel out the cosine thetas. But I do see this. I have a 1 minus sine squared. What is 1 minus sine squared? Ooh, if I rearrange this, 1 minus sine squared. Oh, it's just cosine squared, okay? So I have a cosine squared theta, and then I still have this plus cosine theta. All over 1 plus cosine theta. Alright, well, hopefully we're starting to see where this is going. I know that if I have cosines in both terms, well, I can factor out a cosine theta, which would leave me with cosine theta plus 1 all over 1 plus cosine theta. And now, I know it's not quite the same, but can you add in any order you want? Yeah, you sure can. 1 plus cosines are going to cancel, and so my final answer is just cosine theta. Alright? So again, we need to be able to work from all of our different steps. First, I did common denominator. Then I used my Pythagorean identities. Then I factored. Then I canceled. Alright? Okay. Now, in number 7, there's nothing great at the beginning here. I can tell because I don't see any squareds. Because I don't see tan squared x, there's no identity I could really work with yet. You could go to sines and cosines, but to be honest, I think that's just kind of muddying this problem up. So what I would say is if I see this whole term being squared, and I see this whole term being squared, why don't I actually do that distributing to see what I have? Alright? So I'm going to have tan x plus 1 times another tan x plus 1. And then I'm going to have a tan x minus 1 times another tan x minus 1. Alright? When I go and I distribute this, I'm going to end with tan squared x, and then I'm going to have outers and inners. Oh, I'm going to have 2 tan x, positive 2 tan x, and then plus a 1. Then over on this next piece, I'm going to have another tan squared. This time when I do tan x times negative, okay, I'm going to have minus 2 tan x. And then I'm still going to have another plus 1. Alright, so what's pretty awesome about this, hopefully you guys see, is if I have a positive 2 tan x and a negative 2 tan x, I can cancel. And then I'm really hoping that you guys see this. If you have tan squared x plus 1, tan squared x plus 1, ooh, this is just secant squared. And then I have tan squared x plus another one. Ooh, this is another secant squared. And so the last thing to keep in mind, please, it already told us that we needed a single term. How do I combine secant squared plus secant squared? No, it is not secant to the fourth, or it's not secant x to the fourth. It's 2 secant squared x, and that is your answer. Okay? Okay, I know this is running long. Let's get to this last one. Call it a day. Alright, so number 8, this is a great example of one where I'm getting a little scared because I see cosecant and cotangent and tangent. That's a little scary to me. I think this is going to be way easier if I get everything into sines and cosines. Alright, so that's going to be my first step. I know that cosecant is 1 over sine, so I write it. I know that cotangent is cosine over sine, and I also know that tangent is sine over cosine. Ugh, that doesn't even look that much better. But at least it got us to a next step. And by that I mean, what do we see in the bottom? I see fractions. How do I add fractions together? I get common denominators, okay? So again, right now, I don't even know what I would do. At least now that I'm here, I have an idea of my next step, alright? So I'm going to multiply by cosine over cosine, and over here sine over sine. Again, why did I do that? Because I needed to have the common denominators. Alright? So let's keep going. I know that I'm still going to have, I'm going to kind of come over here a little. I know I'm going to have 1 over sine. Now what happened when I multiplied this out? I ended up with one denominator of sine theta, cosine theta. But over here, ooh, cosine times cosine, that's cosine squared. And over here is sine squared. Alright. Okay, I'm getting somewhere. This is looking better. Cosine squared plus sine squared, that's a 1, isn't it? Yes, it is. Okay, so now I know that I have 1 over sine over 1 sine theta cosine theta. Sorry guys, I should have maybe spaced that out a little bit better. Sorry. Alright, so at this point in time, I'm hoping you see and say with me that, like, this is just kind of nasty looking, right? I don't like dividing fractions by more fractions. So what am I going to do instead? I'm going to use my keep, change, flip method. I'm going to keep my first fraction, I'm going to change to multiplication, and I'm going to flip my second fraction. Okay? Now, can I cancel sine thetas? I absolutely can. Why? Because I'm not adding things together. This is all being multiplied together, right? If I really wanted to rewrite this, this would actually be, right, because I'm multiplying tops with tops, so sine theta, cosine theta, all over sine theta. You see how that's just multiplication? Alright, when it's just multiplying, you can cancel things out. So I'm going to say goodbye to my sines, and I am left with cosine theta. Alright, so again, I'm sorry for this lengthy video. Yeah, I hope that this stuff is kind of coming back to you, and of course, we will talk in class, and we are going to practice quite a bit. Alright, peace.